that we know what the problem is and we know we're going to use dynamic programming to solve it, as always our first step will be to construct or set up the initial DP table. Now in a matrix chain multiplication problem, the input given to us will be this array consisting of the dimensions of the matrices. So like I said, your number of multiplications depends only on the matrix dimensions or the orders of the matrices, not upon what are the actual numbers present inside the matrices. So the only inputs that will be given to us are the dimensions of the matrices. So here we have 4 matrices, A1 which is 30 cross 35, A2 which is 35 times 15, A3 which is 15 cross 5, and A4 which is 5 cross 10. So and the product we wish to compute is A1 cross A2 cross A3 cross A4. You can see from the dimensions that they satisfy the rule or the compatibility required for computing a product. So when these are the matrices, this array containing the dimensions is given to us. So 30, 35, 15, 5, 10 in that sequence, and each value is given only once. There's no repetition. We call this array P. Now this is the only input given to us, and generally in all the examples I've been teaching you so far, I made this claim that the dimension of your DP table is equal to the number of input parameters you get. So here I would like to make a contradictory statement. Although you have only one input, which is this array, we will make a 2-dimensional DP table because we are going to be multiplying at least 2 matrices at each step. So that is the reason our table here will be 2-dimensional. So it will be an n cross n table where n is the number of matrices. So here if you have 4 matrices, then you will have 4 columns and 4 rows, and we will only be filling in the upper triangular part of the table. The diagonal, the leading diagonal and everything below it will be 0. So I will explain why very shortly, but as of now just understand that this is the DP table setup. So what I want you to know when you look at this slide is 2 things. One, the input given to us will be an array containing the dimensions of the matrices in the order in which they have to be multiplied. So if you want the dimensions of the ith matrix, you have to look at the I minus 1 and ith elements of this array. So you take A1, which is the first matrix, I equals 1. So its dimensions will be 30 cross 35, which is the 0th and first elements of this array. Similarly, if you want the dimensions of any matrix I, you look at the positions I minus 1 and I in this array. That gives you the dimensions of that matrix. So this is one thing you need to know with regards to the input. With regards to the DP table, we construct a 2-dimensional table where the number of rows and columns is equal to the number of matrices which overall we want to multiply. We will fill the leading diagonal and all lower triangular elements with zeros. The upper triangular elements are the ones we are going to try and fill in. Now we will move on to the optimal substructure and things like that, but before that, as always when you have a DP table, once you've set up the table, the next thing you have to do is define what the value in a cell stands for. So you have to define what DP of I of j represents. So in this example, DP of I of j represents the minimum number of multiplications required to compute the product of matrices from I up to j. So I don't know if this is clear. This is an I plus 1, so on up to j. So going back to our table, if I say DP of 2 of 4, for instance, it means the minimum number of multiplications required to compute A2 cross A3 cross A4. Everything from the ith to the jth to be multiplied. What's the minimum number of multiplication operations you require? So if I say DP of 1 of 6, for example, we don't have a 6 in this matrix, but generally. So if I say DP of 1 of 6, it means the minimum number of multiplications required for the matrix product A1 cross A2 cross A3 cross A4 cross A5 cross A6. And so on and so forth. So that is DP of I of j. Now that you know that, we'll see why we filled in all these elements with 0. The first part we look at is the leading diagonal elements. So if you see DP of 1 of 1, according to our definition, it should mean the number of multiplication operations required to multiply everything from 1 to 1. from matrix 1 to matrix 1, which is just a single matrix in itself. So there is no multiplication at all, so it is 0. And the same thing for 2 of 2, 3 of 3, 4 of 4. Please understand that when I say multiplying from A1 to A1, it does not mean A1 into A1. We are not squaring the matrix here. You have to start from I plus 1 up to j, and here I equals 1 and j equals 1, so there is no progression, there is no sequence of matrices at all, nothing to multiply. So dp of I will be 0 for any number I. So that's why the leading diagonal is filled with a 0. Now coming to the lower triangular elements, dp of 2 of 1, for instance, is the minimum number of multiplications required to perform A2 cross A1. Now if you look at the dimensions, it is amply clear that A2 cross A1 is not supported according to the rules of matrix multiplication. You know there is this constraint. The number of columns in the first matrix should be equal to the number of rows in the second matrix, which is not fulfilled, and which will not be fulfilled by any of the combinations in the lower triangle for any matrix multiplication you take, unless everything is of the same dimension, of course, which is one extreme case which we are not going to talk about. So assuming all the dimensions are different, 2 cross 1, A3 cross A2 cross A1, or 4 cross 3 cross 2, those things will not be supported. So we fill them with zeros as well. So the only things we are left to fill are the upper triangular elements which represent valid multiplication. So that is what this the first part of this slide says. We are not multiplying any matrix by itself. There is no multiplication, so it's a 0 for the diagonal, and j into j minus 1 up to I. So A4 into A3 into up to A1 is not supported according to the rules of matrix multiplication. Hence, we will only fill in the elements of the upper triangle. And this point, I already made it clear. If you want the dimensions of the ith matrix, you want to check the I minus 1 and ith elements of the array.